So looking at having protons in a strong magnetic field, it causes them to precess, and then they precess with a certain frequency. We call that the Lamore frequency. If we send a radio wave into a system that's in precession, so some protons and neutrons that are unpaired and in precession, that Lamore frequency of radiation that we send in is absorbed by the protons, and it's a process called resonance. And this causes the proton's magnetic alignment to flip from the spin that it's doing round to another state of spin. If you think of it like a top being flipped from its normal spinning position over to its side into a less stable position, and this is called spin flip or resonance. That spinning proton then flips back and it releases radiation, electromagnetic radiation, radio frequency waves at that Lamore frequency. Similar systems of oscillation, two oscillating systems can have resonance. So if you look at the picture there, the guitar string, if you pluck one string, the other string next to it that you haven't plucked starts to vibrate also, and that's waves from, they have a natural frequency, and that energy can be passed from one to the other. And so those hydrogen protons also have that effect. If we look at this picture here, we can see the spinning hydrogen, and when a radio frequency is sent in by radio coils, it flips down and then it flips back up again and releases that radio wave or that radio signal. So spinning in precession, radio wave sent in, flipping occurs, precession turns on its side, and then it flips back, and then a radio wave is released. So we can get every proton that's unpaired to flip and then flip back and release its energy, and that energy can be mapped, and the time it takes to flip back are what we call these T1 and T2 times, and we'll see those a little later. If we look at the picture, here we have a diagram, video, and I'll just press play here and you can see we've got these precessing tops. Now this is different to the system that we've seen, which is using a magnetic field to cause precession. Here we've got gravity and spinning tops. So now if we send in a radio wave at a particular time, a particular frequency, the Lamore frequency, which is equal to this spinning frequency, about 85 megahertz. So when they're spinning, we send in our radio wave, and the unpaired ones will flip over. You can see that happen here. So they've flipped over, they absorbed the radio wave, and then they'll flip back. And when they flip back, they release that radio wave that was sent in. And that radio wave or radio transmission, radio frequency, is at the Lamore frequency. And we can change that Lamore frequency by changing the magnetic field at certain places. So we're getting these unpaired protons with net spin, so such as in hydrogen, flipping and then releasing that radio wave. And this is, you can see the whole process just quickly. So we've got precession, whereas in this case the magnetic field is in this direction across Okay, and then we'll start the process. So that magnetic field causes precession. Then in comes the radio wave, and they flip up, then they flip back, and out comes the radio wave, or radio frequency. It's just an electromagnetic radiation. Okay, just show you again. So that was the flip and the flip back. Radio wave in, flip, release, flip back. And the time it takes between the radio wave coming in and the flipping back and releasing that radio wave is the T1 and T2 times. And they're going to be discussed later, just briefly, but different molecules, different cases of where the protons exist, such as in carbohydrates, or in water, or in a tumour, or in other cases, these hydrogens have different relaxation times, and we call that, as it flips back, the relaxation time. Okay, so there's many other medical techniques. The contrast in an MRI is strongly dependent on the way the image is acquired. By adding radio frequencies or gradient pulses, by careful choice of timings, it's possible to highlight different components of the object that we're imaging. Because we rely heavily on hydrogen, the MRI is not quite as good for looking at bones, skeletal imaging, as X-rays or CT scans are. That proton spin density, that change in proton spin and the relaxation times, is good for looking at different tissues, such as soft tissues. For example, grey matter in the brain and white matter have different characteristics, and they can be looked at because they have contrasting images on an MRI scan.